Hello, welcome to this video. It's the second of a series on drawing shear and moment diagrams using graphical method. So there was a video before that where I explained the theory and the proof of the graphical relationships between V and M. So there's the derivative relationship and there's the integration relationship. So let's jump right away into this example. We have a simply supported beam, a hinge at A and a roller at B with distributed load W, uniformly distributed load for a length L of the beam. Of course, before you draw the shear and moment diagrams, you have to figure out the reactions of the supports. So I have A and B, and this is a symmetrical beam, so I have WL over 2, WL over 2 for both reactions here. So when you draw the shear and moment diagrams, you draw the zero line or datum line for the shear and moment diagrams here. Above the line is positive, below the line negative. And then I start with the shear. So you always, in the graphical method, you can't draw the moment before the shear. You have to draw the shear first and then use the shear diagram to draw the moment diagrams. So you start with the shear and you start from the left. So the process starts, it's better to start from the left. You can do it from the right, but it will be a little complicated compared to the things we explained in the first video. So you have to change a little what you learned in the first video to be able to draw the diagrams starting from the right. So take my advice, start drawing the diagrams from the left of the beam. And then when you start doing the shear diagram from the left, whatever force goes upward, then the shear diagram jumps up. And when a force goes downward, then the shear diagrams drops. So this is why when I start from the left, I start with 0, but just that 0 value here is just before the beam, right before the beam support. And then once I hit the support, I jump up by WL over 2. So VA is equal to WL over 2. And then when I look here at the beam, what would be the next discontinuity point or the point of interest where I want to calculate the shear? Because there is no intermediate point load or moment, then I would direct my attention to the end of the beam, point B. The distributed load here is a continuous load uniformly distributed, so there is no point in the middle that I expect to have a discontinuity here. So now the difference between the shear value at A and B, so the difference of the shear between these 2 points, would equal to the area under the load curve. The load curve here is simple, it's just a horizontal line with a height W and the length here is L, so the area is WL. But remember that the difference between 2 points is equal to negative the load area. So it's negative AW, so this means that if I start with VA is equal to WL over 2, I will drop by negative WL until point B. So this means that the VB would equal to WL over 2 VA minus plus delta VAB that I calculate, and this delta is negative, so I'm dropping here by negative WL, which means that I end up with the same WL over 2 but negative. And then this negative here value is just before the reaction at B. So whenever I hit the reaction at B, I will hit 0. But if I try to connect between these 2 points now, WL over 2 and negative WL over 2 between points A and B, when I connect it, should it be a parabolic curve, or what would be the shape of the curve for the shear diagram? It will be a line, a constant with a constant negative slope. Why is that? Because W has a constant value between A and B. And the W is positive, but remember you flip the sign for the relationship between the load and the shear. So now this translates into a negative constant slope. A negative constant slope geometrically is equivalent to just a line going downwards. So you're going downwards linearly from WL/2 to negative WL/2, and then this value, like I said, it hits the reaction, so it brings it to 0. Whenever you go back to 0, so you start with 0 and you end up with 0, that's a good sign. That's good. That means that your calculations add up correctly. So it's kind of a free check for your solution. At the end, you end up with 0 if you start with 0. So once you have the shear diagram, you can start drawing the moment diagram. But before you start drawing the moment diagram, you might look into an additional point of interest, especially when the shear curve or diagram intersects with the 0, with the axis here. Because if this is a 0 shear value, and remember we know that the relationship between shear and moment is the slope, that the shear value at any point is the slope of the moment at this point. So the a 0 shear value is a 0 slope for the moment. So that's a very interesting point, because the 0 slope means the maximum value for that curve, for the moment curve. So how to find this intersection? I can see that from symmetry it's intersecting at the middle of the beam. But if I want to calculate this point generally, is that you will use the rate of dropping of that drop in the shear curve, which is basically W, right? So W here is the rate that you drop from WL/2 to negative WL/2 at the beginning and the end of the beam. So what does it take to drop WL/2 to 0? To be basically equal to the shear value at the beginning, which is WL/2, divided by the rate of the drop, which is W. So you end up with L/2. So that matches with our previous conclusion that's from symmetry, it's in the middle of the beam. So now once you get the location of that point, the 0 shear point, now we can move on to drawing the moment diagram. And you start from the left with a 0 value, and then you see here that it will stay 0, unlike the shear when you start with 0 and jump with the reaction. Because I don't have a fixed support at A, so there is no point moment reaction at A, or maybe there is no, like if there is a load at A as moment, then I will have a jump or drop at of the moment diagram at A. But this 0 will stay 0, but will change from the 0 value with the slope, positive slope, that's equal to positive WL/2. So it will stay 0, but it will increase here with the rate initially WL/2. But that rate, that slope, decreases. So because the shear value over the length of the beam now drops. So until it reaches a 0 slope at point C. Now what will be the change of the value between A and C? It will be equal to the area under the curve of the shear between A and C. So I'll call this area here A1. And this A1 would equal to basically the area of a triangle. It's half of the height WL/2 times the base L/2. So that will translate into positive WL²/8. It's a positive area because you're dealing with the positive shear values here. This means that the shear, the moment value will jump or increase from A to C by a value of WL²/8. Now, how to connect between these 2 points? I know that the initial slope is WL/2, but also I know that the end slope is 0 slope. And now I can visualize that my parabolic shape here, you have a high slope at point A, and then it starts to decrease, the slope decreases until it hits a 0 slope. So that makes sense now. Now, if you think about what would be the next point of interest to draw the moment, it will be the end of the beam. There is nothing happening between the middle of the beam and the end of the beam. There is no discontinuity point. So now I will need to calculate A2. And A2 here is from symmetry. I can calculate the area in detail, but I know it will be equal to negative A1, because now I'm dealing with a negative shear value of negative WL/2. So A2 will be equal to negative A1. So this means that I'm a delta M between C and B is a negative value, so I'm dropping. The value here drops from WL square over 8 by a delta value of negative WL square over 8. So you drop to 0. MB is equal to 0. And like we had in the shear diagram, when you hit 0 at the end of the beam, the right end, this is a positive sign. That's kind of a smiley face here. Now, how to connect between these 2 points at moment MC and MB? I know that I start with a 0 slope at C, because I have 0 shear there, and then that slope is increasing in the negative. So the value of the shear keeps increasing in the negative, so the slope increases in the negative. So you start with this, and then you're sinking down the moment here until you hit point B. The maximum slope here is negative WL over 2. So you end up kind of a symmetrical, also parabolic shape for the moment. So that was a quick example here to show you how to draw shear moment with a very simple beam. And actually, over time with practice, you will find that simply supported beam with a distributed load, you can just right away draw the shear moment. You don't have to start from scratch. I know that I'm jumping up by WL over 2, and the maximum moment is in the middle, and it's equal to WL square over 8. These values will be kind of almost, you will memorize it because of the practice, and many cases in practice you see such beam in different systems and different buildings and different frames and machines and all of that. So that's it. So thanks for watching. I will see you in other videos to see maybe another example of drawing shear moment diagrams using the graphical method. Thanks for watching, and take care.